Hello, we're in Monaco. Why are we in Monaco? Obviously to see the Monte Carlo casino. Why else would we be in Monaco? Why else would we be in Monaco? And so we stumbled upon these cannonballs, which is a pretty cool math problem. Come over here, let's look at how many layers there are. We see each layer has a perfect square number of cannonballs. 1 squared, 2 squared, 3 squared, 4 squared, 5, 6, 7, 8, all the way up to 8 squared. So my favorite thing in the world is little Gauss's formula, summing up 1, 2, 3, 4, 5, 6, 7, 8, and so on. But this time we're squaring each terms. And I can't remember what the formula is, but I know that it's very much like integrating x squared. So we're integrating x squared from 0 to 8, which is something like 8 cubed over 3. So 8 cubed is 512 over 3. I'm missing the low order terms. I'm missing the quadratic and linear terms, but I've got the cubic term correct. So anytime you're summing up powers of the integers, it's just like integrating them. That will get you the first order term correct. So that's your ballpark estimate, 512 over 3. And you can, maybe I'll work out the details at home or something like that. But here's a cool problem of sum of squares. And let's enjoy the beautiful coastal view of Monaco. Monte Carlo Casino coming soon. Here are the details for the sum of the first n kth powers. So it's 1 to the k plus 2 to the k plus 3 to the k up to n to the k. So the first term is the calculus term, just by integrating. If we're integrating, x to the k, we get x to the k plus 1 divided by k plus 1. So here's the calculus term. That's the leading order term that I came up with. This is true for all k. And then there's this correction term, which is just half of the last term in the series. The last term in the series is n to the k, so we have half that. Plus we have these low order terms in terms of n to the k minus 1 all the way down to a linear term. So in our case, we were summing the squares, the first n squares. So this was the term I got correct, the calculus term. And so this is from Faulhaber's formula. You get this second term is always half the last term. So there's a nice correction here that's easy to remember that's independent of k. This coefficient is always 1/2. And then the lower order terms here are a little bit more difficult to come up with. But in this case, since I know the sum of the coefficients is 1, since I know when I plug in 1 in this formula, I have to get 1. That means the sum of the coefficients is 1. So we have a third plus a half. So the only thing left over is a sixth. So here's the formula, the exact formula for the sum of the first n squares. And so if we wanted to know the sum of the first 8 squares, so I got this 8 cubed over 3 part. Then the correction is the half of the last term, so the last term is 64, so half that is 32, and then this linear term is really small. So the exact number of cannonballs is 204. So, but just learning these first 2 order terms is a good thing to do, and then if you want to, you can look up the low order terms. But it's easy to memorize this, because this one is from calculus, and this is just half the last term, and this always works for every k. And thank you very much. Up there is where we're doing the cannonballs. Up there, we're counting cannonballs.